so we're in section 12.1. Talking about tangents to circles. So first off, we need to know what we mean when, so we're not talking about tangent like we did when we talked about trigonometry, what we mean by a tangent. So a tangent to a circle is, it can be a line, it can be a segment, it can be a ray, but I'll just say line. So I'm going to say a line, and we're in the plane of the circle. So we're not in 3D anymore. We're back in the plane. We're back in 2D. A line in the plane of the circle that intersects the circle in exactly one point. So if we had a picture, to draw a picture of our tangent, we would have our circle like so, and then our tangent line would look like this. And call that point P, and I'm going to call this line, call this AB. So we call AB the tangent line. And I'm just going to draw an arrow. So this is the tangent line. We could have a tangent segment, we could have a tangent ray, we could have a tangent and a tangent line. And this point P we call the point of tangency. Or the tangent point. So the line comes just close enough to the circle to touch it in exactly one place. Tangent lines are very important as you move on in math. One of the two big ideas in calculus, when you get to calculus, has to do with tangent lines for curves, for graphs of equations. So this idea of a tangent line, something that intersects in exactly one point, is a really important idea that we're going to work with in this chapter. And tangent comes from the Latin, means to touch. So it just touches that circle. So some interesting things happen when we have a tangent line to a circle. So we're going to talk about a couple of theorems. What happens in chapter 12 is we're moving away from formulas and equations that we're plugging numbers into equations. Find our answers. We're moving back a little bit more to working with theorems and what that tells us about shapes. So we're going to be figuring things out. There are, in chapter 12, we'll be talking about a couple of proofs. So we'll be doing proofs again. So, and then the other thing that happens in chapter 12 is a lot of things that we've talked about in the past, we start using it all together with these problems. So a lot of things we've talked about already come back in chapter 12. So let's talk about our theorem. So we know what a tangent to a circle is. Let's talk about our first theorem. I'm just going to call it the tangent theorem. And the tangent theorem tells us that if a line is tangent to a circle, then it is perpendicular to the radius of the circle. Not perpendicular, tangent. If a line is tangent to the circle, then it is perpendicular to the radius. at the tangent point. So our picture here looks like our picture before, but we're going to draw a radius now. So if I have my tangent line like so, and there's my tangent point, P, and I'm going to call this line AB. And here's my center, so we'll draw a radius. What the tangent theorem tells us is that this angle is a 90-degree angle. Call that point O. So line AB is tangent to the circle. The circle O. That tells us that line AB is perpendicular to segment OP. So we have a 90-degree angle there. So this is really the main idea, the big idea with tangents and circles, is that where the tangent line, the tangent segment, whatever, where it touches the circle, we draw a radius to that point. The tangent line and the radius make a 90-degree angle. A couple of important ideas about radii of circles that we use a lot in chapter 12. So a couple of things that we'll use to solve problems. One is all radii of a circle are congruent. So any radius that we draw in a circle is going to be the same as any other radius in the circle. So it doesn't matter where we draw it, they're always congruent. And that comes up in solving problems a lot. And in this chapter, when in doubt, draw a radius. So we can draw in a radius to the circle to help us solve problems. So kind of like when we talked about similarity, we said when in doubt, write a proportion. When we're dealing with circles, when in doubt, draw a radius. And we'll use those as we go through a couple of examples here. So any questions on what the tangent theorem is telling us? Okay. A couple of examples. So the first one, here's our setup. We have this circle, and we have a couple of tangent segments, like so, that intersect out here. There's my center. And we're going to say that this is 152 degrees. And that angle is x degrees. I'm going to call that A, D, C, and O. And we're going to say for this problem that segment AD and segment AC are tangent to the circle. We want to find x. So, what are we going to do here? Well, the problem tells us that AD and AC are tangent to the circle. What does that tell us about these two angles here? Each one is, what kind of angle is this? 90 degrees. Tangent line is perpendicular to the radius. These are radii. So this is 90 degrees, and this is 90 degrees. What do all angles inside a quadrilateral add up to? 360. So we have three of the angles of this quadrilateral 1, 2, 3, 4-sided shape. We have 3 of the angles. All 4 of the angles have to add up to 360 so we can find the 4th angle. So 90 plus 152 plus 90, these 3 angles. When I add those together, I get 332. All 4 of the angles have to add up to 360. So 360 minus 332 is 28 degrees. So x equals 28 degrees. So we used our tangent theorem. Those 2 angles had to be 90-degree angles. And then we remember that all the angles inside a quadrilateral, 4-sided shape, add to 360. Questions there? All right, let's look at another one. Similar kind of problem. So let's say we're in a plane, 6.5 miles above the Earth. And we want to know how far can we see on the surface. So how far away is the horizon? So that just asks the question 2 different ways. How far can we see? That's asking us how far is a horizon. And we're going to say the radius of the Earth is about 4,000 miles. Well, we don't have a picture, so let's draw a picture. So here's the Earth. There's my Earth. Here's my plane up above the Earth. This is not drawn to scale. And it tells us, the problem tells us that's 6.5 miles. And we know that the radius of the Earth is 4,000 miles. And the problem asks us, how far away is the horizon? How far can we see? So it's asking us, if I draw this segment here, right to the tangent point. So we can see to the tangent point. If we look closer than the tangent point, we're going to see less far. And if we look beyond the tangent point, we're not looking at the Earth anymore. So the farthest we can see is to the tangent point. We can see to tangent point. So we have part of the information we need. So this is one of the problems where if we don't know what to do, let's draw in another radius. So I'm going to draw in another radius from the center of the Earth to the tangent point. All the radii are equal, so that side of the triangle is 4,000 miles also. And what angle does the radius make with the tangent line? 90 degrees. Well, now I have a right triangle, and I know 2 sides of the triangle. So what can I use to find this missing side? We can use the Pythagorean theorem. So this is my 90-degree angle. So this side is the hypotenuse. This is the longest side. So I have x squared plus 4,000 squared equals, and this side is 4,000 plus 6.5, so I get 4,006.5 squared when I use the Pythagorean theorem. So x squared plus 4,000 squared is 16 million. And this equals, and this comes out to 16,052,000 42.25. Subtract 16 million from both sides, and all I'm left with is this 52,042.25. So x squared equals 52,042.25. All I did there was subtract the 16 million from both sides, and take the square root to undo that square, and I get x equals 228.1 miles. So I can see about 228.1 miles to the horizon along that side of the triangle. Questions there? All right, so let's talk about the converse of the tangent theorem. And remember, to make a converse, we just switch around the if and the then. So for the converse, we're saying we know that this line or this segment makes a 90-degree angle at the radius. If that's true, then that tells us that line or segment is tangent. So we're just turning it around. So we're going to say if a line is perpendicular to a radius, then it is tangent to the circle. At the endpoint of the radius. So our picture looks exactly the same. We're starting out not knowing that the segment or the line or whatever is tangent to the circle. All we know to start out is that it makes a 90-degree angle. So our picture looks like this. So we know that angle is a 90-degree angle. I'm going to call this O and P, and A and B. So we're saying that line AB is perpendicular to OP, segment OP. Then line AB is tangent to the circle O, at P. So if we know that angle is 90 degrees, that guarantees us that we were talking about a tangent line. All right. Questions about our converse? Okay, let's look at a couple more problems involving tangents and circles. So here's our setup for this problem. We have a circle. And this is a 90-degree angle. And we're going to say this is X, this is 24, and this piece here is 18. we want to find x. Well, we know we have a 90-degree angle here. So since we have this triangle with a 90-degree angle, what are we going to want to use? We want to use the Pythagorean theorem. We only know this piece of this side. We don't know the whole side. How can we figure out the whole side? No, that we can't just subtract. But can we figure out this piece? That's a radius. So that is x. So that piece is x. So we can figure out all three sides. This side is the hypotenuse. So we have x squared plus 24 squared equals, and what's the length? What's the entire length of this side? 18 plus x. And we're going to square that. So I'm going to say that x squared plus 24 squared is 576. When I square parentheses, I can't just distribute the square. This is the same as saying 18 plus x times 18 plus x. And what do I have to do when I multiply parentheses out like this? What's that? FOIL. I have to FOIL. So let's write that out over here, just so we can keep track of it. F-O-I-L. The first, 18 times 18. So I'm multiplying the first things in the parentheses. 18 times 18 is 324. The outside, 18 times x. Inside, 18 times x. And the last, x times x, equals x squared. And I add all of these together. So I get x squared plus 576 equals, and I'm going to write it in this order to start with the x squared, equals x squared. 18x plus 18x is 36x. And then I have a plus of 324. I can subtract x squared from both sides. Those go away. And I get 576 equals 36x plus 324. This is easy now. Subtract 324. I'm going to turn this around. 36x equals 576 minus 324 gives me 252. Divide by 36. Let's go away, and I get x equals 7. Yes. All right, questions there? All right, let's look at another similar kind of problem. But we kind of have to go the opposite direction here. So for this problem, they give us this information. And we know that this is 5, this is 12, and this piece is 9. And we want to know is segment AB tangent to the circle? So this looks kind of like our last problem, and we want to use a similar process to solve it. If this segment is tangent to the circle, what would that angle be? That would be 90 degrees. How can we tell if that's a 90-degree angle? If that's a 90-degree angle, this would be a right triangle. And what always works for a right triangle? Pythagorean theorem. So what this problem is asking us to do is test the Pythagorean theorem. So it wants us to put the sides of the triangles in the Pythagorean theorem and see if a squared plus b squared equals c squared. If it does, for this triangle, then it's a right triangle. If it does not, then it's not a right triangle. All right, so if this side is 9, how do we figure out the whole side, this whole side of the triangle? What's this piece? 5. That's also a radius, so we know that is 5. So this whole side of the triangle, 9 plus 5 is 14. This would be the longest, this is the longest side, so that has to be the hypotenuse. So we want to see if 5 squared plus 12 squared equals 14 squared. 5 squared plus 12 squared, 25 plus 144 is 169. 14 squared is 196. So a squared plus b squared does not equal c squared. So it's not tangent, because that does not make a 90-degree angle. If it were a tangent to the circle, that would make a 90-degree angle, and the Pythagorean theorem would work for that triangle. Kind of like the last problem, just working it backwards. All right, questions there? Okay, last theorem for this section. This one doesn't have a special name, so we're just going to call it a theorem. Another theorem about tangent segments and circles. I don't want to draw my picture yet. So this theorem says that if we have two tangent segments to a circle that intersect outside the circle, so they have a common endpoint, outside the circle. If that's the case, the two segments are congruent. So our picture for this one looks like one of the problems we did over before. So here are my two tangent segments. Let me redraw that one. There we go. And I'm going to call this A, B, and C. So what this says is that we know that segment AB and segment AC are tangent to the circle. If that's the case, then AB is congruent to AC. All right, and let me sketch out really quickly how we could figure this out. So how we would go about proving this. So this is one of the cases where we're in doubt. We're going to draw in a radius. I'm going to draw in a radius there. I'm going to draw in a radius there, and I'm going to divide this into two triangles. These two segments are tangent to the circle, so we know those are 90-degree angles. All radii are congruent, so those two sides of the triangle are congruent. This middle piece is congruent to itself. So we have a hypotenuse and a leg of this right triangle, congruent to a hypotenuse and a leg of that right triangle. So these two triangles are congruent. So these long sides of the triangles have to be congruent as well by CP/CTC. Corresponding parts of congruent triangles are congruent. So easy proof to show that those two segments have to be the same if we have two tangents to the circle. So we end up working with circles, turn circle problems into triangle problems, and then the stuff that we've learned about showing that triangles are congruent comes back in problems about circles. It's kind of nice. All right, let's look at one last example using this idea of these two tangent segments. So for this problem, we're going to have a circle that's inscribed in a triangle. So here's my triangle. So there's my setup, and we know that the circle is inscribed in the triangle. So that tells us that the circle is tangent to the triangle at those 3 points. So that's what inscribed means, is that it only touches the sides of the triangles in 1 point. So each side of the triangle is tangent to the circle. And we know that this length is 14, this length is 8, this is now drawn to scale, this length is 5. And we want the perimeter of the triangle. Well, if we look at this corner right here, we have two segments that are tangent to the circle, and they intersect at a point outside the circle. So it's just exactly what the last theorem was telling us about. Two tangent segments, they have a common endpoint outside the circle. So what does the length of this piece have to be? It also has to be 8. Here are two tangent segments that have a common endpoint outside the circle. So what does that piece have to be? 5. And this piece, two tangent segments outside the circle, that has to be 14. So our perimeter, all of these added together, 14 plus 8 plus 8 plus 5 plus 5 plus 14. Add those all together and I get 54 units for my perimeter. And we can figure that out because we know that these segments are tangent to the circle. So these pieces have to be the same. Questions there? All right. Homework? All right, there we go.